Welcome my friends, welcome to my next lecture. Now for this lecture, my plan is to talk about when a function a possesses an antiderivative. So in my last lecture, I was talking about if suppose suppose you start with a function small f and suppose there exists a function capital F such that capital F prime is equal to small f, then we have seen the corresponding contour integration starting from Z1 and ending at Z2. It is independent of the choice of the contour. Now for today's lecture, I will give some conditions on my functions small f and some domain so that I can say that yes, if my function satisfies this kind of properties, then antiderivative or primitive always exist. So once I have that one, you will see that to talk about that one, I need the use of what is called Cauchy-Goursat theorem that I have already discussed. So then I will come to what is called Cauchy's integral formula. Then as a consequence of Cauchy's theorem or Cauchy's integral formula, we will have Cauchy's estimate and Liouville's theorem and Morera's theorem in later on. Okay, so my plan for today's lecture is to give some conditions on my function small f so that I can say that yes, if this satisfies, then small f always possesses what is called antiderivative and primitive. Yeah, so as I said, so this is the kind of questions I would like to investigate. So that's what I have written. The question is that under what conditions on my function small f we can always guarantee yes, if my function small f satisfies these properties, then there always exists capital F such that capital F prime is equal to small f, or small f possesses what is called antiderivative. To do that, I just recall some definitions. I have already discussed this kind of definitions, like if I have a domain, when I say that the domain is simply connected, and if the domain is not simply connected, then it is a multiply connected domain. Now if you recall what is simply connected domain, our domain is called simply connected. If I take any simple closed contour inside my domain, it what is called encloses only points of D. Right? Or in other words, I can squeeze my simple closed contour to a single point inside that domain without leaving my domain D, or without passing through any singularity. So this is kind of domain, it's called simply connected. Like if I have an open unit disk or complex plane, or maybe later on I will discuss the right half plane, these are the domain are simply connected domain. Or if I have a simple closed contour, the interior bounded domain is the simply connected domain. And if I have a domain and if there is a hole, this kind of domain is not simply connected, because if I take a simple closed contour around the hole, then I cannot squeeze it to a point without leaving the domain, because at some point of time you can away from the domain, or the domain or the portion bounded by this simple closed contour, it contains some point which is not a part of the domain. So this kind of things I've already discussed. So our domain is called multiply connected if it is not simply connected. For example, the sets full complex number, open unit disk, the right half plane are all simply connected domains. However, if I have a domain, there is a puncture, like punctured complex plane or punctured open unit disk. So these are the annulus. These are not the what is called simply connected domain, because there are holes inside that domain. Okay. Now this theorem I already discussed and proved. This theorem, Cauchy-Goursat theorem or Cauchy's integral theorem. Now you will see later that this theorem ensures us that if I have a function small f satisfies these properties, then small f always possesses what is called antiderivative. Now what is that theorem? You are already familiar with this statement of this theorem. This is called Cauchy-Goursat or Cauchy's integral theorem, or Cauchy's integral theorem for simply connected domains. It says that if I start with an analytic functions in a simply connected domain D, then the conclusions of Cauchy's theorem says that whatever simple closed contour you can take inside the domain D, the value of the contour integrations will give you 0. And that will tell you, this will tell you the existence of what is called antiderivative of your function small f. So of course you will see this will tell you what is called if I take any 2 points Z1, Z2 inside the domain, that means first of all the contour integrations is path independence. That means whatever contour I can take Z1 to Z2, the value of the contour integrations will be same. That means I can talk about this kind of integrations. So fixed a complex number W0 to Z, f of W dW. So this kind of integrations I can define, and if I say that this is my function's capital Fz, then I will show that this capital F is differentiable and derivative of f is exactly equal to small fz. Okay, so therefore this theorems, Cauchy-Goursat theorem or Cauchy's integral theorem, will allow you to have the existence of primitive or antiderivative of my function small f. First, let me see if I take any 2 points in the domain, how the contour integration is independent of the choice of my contour. So this is the one. Okay, before that, there are some examples I have discussed using this Cauchy's theorem. It says that, so consider this kind of contour gamma t to the it, t runs from minus pi to pi, so therefore it is a unit circle if you draw it in the complex plane. So first, for example, you can say that this kind of contour integrations, you don't have to calculate the contour integrations, but whatever machineries I have discussed in my earlier lectures, then you can easily calculate. It says that integration c f z dz is 0 if f of z is equal to 1 by z square or cos square z, and so that means what? That means either you can directly calculate the corresponding contour integrations because you know the parameterizations of your contour and you know your functions, that is one of the way, or you can use some theorem. For example, it says that if I consider like 1 by z square. Now since 1 by z square, it will have an antiderivative like d dz of minus 1 by z. So therefore, I already said that if your function small f possesses antiderivative, then integration z1 to z2 small fz dz, which is nothing but capital F of z2 minus capital F of z1, while capital F derivative is small f. So therefore, since minus 1 by z or 1 by z square possesses antiderivative, or minus 1 by z is the primitive or antiderivative of 1 by z square, using the earlier discussions, you can easily calculate this one. Now since C is a simple closed contour, it is closed, so therefore the integration value will be 0. Similarly, if I have a cos square z, it is also like possesses antiderivative, and since my contour is closed contour, simple closed contour, so therefore the corresponding contour integrations will be 0, because contour integration means what? It should be value of your antiderivative at z2 minus value of your antiderivative at z1. Now you will have minus pi to pi, right? So therefore what will happen? So this if I say that minus pi to pi, okay, so therefore if I calculate integration c cos x squared z dz, what is that? By definitions, this is nothing but integrations minus pi to pi. So minus pi to pi, what will happen? So therefore cosec squared z, z means what? Gamma t squared, then gamma prime t dt, and since it possesses the minus cot of z is the antiderivative, so you can say that this is nothing but by existence of the antiderivative, you can say that. So this is same as, okay, so this is same as integration c cos square means what? So d dz of minus cot of z dz, because it possesses antiderivative, and then what is the value? You can say that this is nothing but cot of at z at 2 points, right? C is a simple closed contour, it's starting from 1 and ending at the same point, so therefore you can say that this is cot of gamma of pi minus plus cot of gamma of minus pi, right? This is the value I already know. So therefore, why know? Because z1 to z2 fz dz, which is nothing but if it possesses antiderivative capital F of z2 minus capital F of z1. So therefore, since it is possesses antiderivative, so therefore this is minus cot of gamma pi minus of minus, that is plus cot of gamma of minus pi, but gamma of pi which is same as gamma of minus pi, so therefore this is 0. Okay, so fine. So therefore, so 2 ways you can do that. Either if you somehow convince yourself, yes, it possesses antiderivative, then use this formula, or you just use the simple definitions of contour integrations. That since you know the parameterizations, you just use the definitions, you will be able to conclude it. But there is a kind of little note, you can check it. Note that here Cauchy's theorem cannot apply it as the integrations are not analytic at 0. So that means what? It says that the functions you are dealing with, like 1 by z square or cosec squared z, that means 1 by sine squared z. Now at 0 it will have a problem, right? So therefore my function is not analytic at the point 0, right? Now what is your Cauchy's theorem says? Cauchy's theorem says that if I have a simply connected domain and if my function is analytic, then if I take any simple closed contour, then the corresponding contour integrations value is 0. But here this is not the case, because here I have a function f of z which is 1 by z square, but here my domain is c minus 0. Okay, so this is not a simply connected domain. This is actually multiply connected domain, right? But so therefore I cannot have it. I cannot apply my what is called Cauchy's theorem or Cauchy-Goursat theorem. The things I have discussed, because of course if I consider the domain C, which is simply connected, but my functions f of z, which is exactly equal to 1 by z square, which is not analytic. So therefore I cannot apply Cauchy-Goursat theorem. However, if I take a simple closed contour inside the domain C minus 0, but still I can have the value of the contour integration is 0. And how this follows? Because if I consider my domain C minus 0, which is a domain, of course, punctured complex plane, and the functions I am integrating, which is 1 by z square, it possesses antiderivative, and C is a simple closed contour. So therefore, by definitions, whatever I have discussed in my earlier, the corresponding value of the integrations is nothing but value of your antiderivative at z2 minus value of your antiderivative at z1, since your contour is closed. So therefore, this is exactly equal to 0. So therefore, this is the kind of conditions. Second is that consider this kind of functions, f of z is equal to imaginary z whole square. Then also you can check that the corresponding contour integration is 0. But what is this functions? F of z is equal to imaginary z square. That means f of z is equal to what is called y square. Now this is highly non-analytic functions. It is nowhere analytic. So therefore f is analytic anywhere in the complex plane. So therefore Cauchy's theorem I cannot apply. So even though my function is defined for all z in the complex plane, but this function is not even analytic functions anywhere in the complex plane. So therefore I cannot apply Cauchy-Goursat theorem to say that whatever simple closed contour I can take, the corresponding contour integration 0. I cannot apply it. However, if I just calculate explicitly using the definition of contour integration, this actually 0. Then what you have to do? So your parameterization is given. So you have to just calculate this object. So what is this? You just calculate it. Okay, if I calculate it, yeah, I will not do the full calculation, just I will give you the formula. So integration C fz dz, what is that? This is same as fz is given, fz is equal to y square, right? So that means by definition of contour integration, that means this is minus pi to pi, then f of gamma t, then gamma prime t dt, right? And what is that? Minus pi to pi. F of gamma t means what? Gamma t is cosine t plus I sine t. Now imaginary part of z, that means it should be sine t, right? So therefore this should be sine square t, then gamma prime t, that means I times e to the it dt. Okay. Now what is your integrand? E to the power it times sine square t, and I am integrating from minus pi to pi. You just calculate in your home, it will give you 0, nothing else. Because you just write e to the it cosine t plus I sine t, then do some algebra, use the typical formulas of what is called trigonometric formula, and calculate it using fundamental theorem, you will get it that this value will be 0. So therefore my point is that sometimes to prove that the contour integration is 0, you should not apply Cauchy-Goursat theorem blindly, because to apply Cauchy-Goursat theorem, you have to see whether your function satisfies the hypothesis of the Cauchy's theorem or not. That means whether your domain is simply connected, whether your function is analytic. There, if I take a simple closed contour, then you can say that by Cauchy's theorem or Cauchy-Goursat theorem that what is called the contour integrations over this simple closed contour is 0. However, if your function, so that is one of the ways to prove that contour integration is 0. But it might happen that even though your function defined on some domain which is not simply connected, but still you can have the corresponding what is called, if I take any simple closed contour in your domain, but the corresponding what is called contour integration still becomes 0. These are two examples which are having this kind of properties. So you don't have to apply to conclude what is called contour integration is 0, but you just use either the existence of primitive, or you can use the definitions of your contour integrations. You will be able to conclude that the corresponding value of the contour integrations. Okay. Now as I said, so consequence of Cauchy's theorem or Cauchy-Goursat theorem, it says that now in my domain, suppose if I have a domain which is simply connected, and if your functions f is analytic, if I take any 2 points z1 and z2 in my domain, then whatever contour I will take starting from z1 ending at z2, the corresponding value of the contour integrations will be independent of the choice of the contour. So that's what it says, independent of path. It says that let D be a simply connected domain, f is analytic, z1, z2 be 2 points in D. Now gamma 1 and gamma 2 be two simple curves joining z1 and z2 such that curve lies entirely in D, then the value of the contour integrations over gamma 1 is same as value of the contour integrations over gamma 2. And there you can at least geometrically if you will see, then you can easily guess, yes, it should be the case. Look, for example, consider this domain D, simply connected. I am considering the point Z1 and suppose I am considering the point Z2. Okay, suppose this is my curve, say gamma 1, one contour gamma 1 starting from Z1 ending at Z2. Now take another gamma 2. That is also a contour starting from Z1 ending at Z2. What my claim is that integrations over gamma 1 should be exactly equal to integrations over gamma 2. Now actually, to prove that one, what I will do, I will apply Cauchy-Goursat theorem. Now to apply Cauchy-Goursat theorem, what you have to do? That means D is simply connected given, F is analytic given. Now what is Cauchy-Goursat theorem? It says that if I take any simple closed contour, then the integrations of or contour integrations of F over this simple closed contour is 0. Now look, I have two contours. One is gamma 1 starting from Z1 ending at Z2, and I have this another contour gamma 2 starting from Z1 ending at Z2. Then what I will do, I will take a new contour gamma, which is nothing but I am starting from Z1 going to Z2 and then I will come back from Z2 to Z1. So therefore what I will do, this is gamma 1, that means I am starting from Z1 going to Z2. Now gamma 2 is starting from Z1 ending at Z2, but what is minus of gamma 2? Given a contour, I can define minus of that curve. Now if C is a contour starting from Z1 ending at Z2, minus of C will be in the opposite. That means it should start from Z2 end at Z1. So therefore I will say that this is gamma 1 union minus of gamma 2. So this is a contour. What kind of contour it is? So it is gamma 1 union minus gamma 2. That means I am starting from Z1 going to Z2 and then coming to Z1. So therefore from gamma 1 I am from coming Z1 to Z2 and minus gamma 2 I am coming back from Z2 to Z1. So therefore this is a contour, but this contour is simple and now this contour is actually closed contour. That means I am starting from Z1 ending at Z2. So therefore now I have a contour gamma. Since gamma 1 and gamma 2 lie inside D, so therefore the contour gamma, this is also lies inside D. And what is the contour gamma? It is a simple closed contour starting from Z1 ending at Z1. My function is analytic in D. So therefore by Cauchy-Goursat theorem says that integrations over gamma fz dz, this is 0, right? But the properties of what is called contour integrations I have already discussed. That means this is same as integrations gamma 1 union minus of gamma 2 f of z dz is 0. But what is this? This is integrations of gamma 1 fz dz plus integrations of minus of gamma 2 fz dz, because if I have two simple contour gamma 1 and gamma 2, and if I join it at the end point, so this is gamma 1 and if it ends at Z2 and minus gamma 2 starts from Z1, so therefore by properties of contour integrations I can separate these two contour integrations. That means this is same as integrations over gamma 1 plus integrations over minus gamma 2, but integrations over minus gamma 2, what is that? This is minus of integrations over gamma 2, that's again the properties of contour integration. So therefore this is integrations over gamma 1 fz dz minus integrations over gamma 2 fz dz, and this is 0 given. So that means what? Integrations of gamma, so this is 0 given. That means integrations or contour integrations over gamma 1 of f same as contour integrations of f over gamma 2. That means this is. So that's the kind of idea. So this the proof I have written. I have written explicitly what will be the corresponding parameterizations. But even though if you just get the idea, okay, that's how you have to make a contour and make out of two contours gamma 1 and gamma 2, you make a new contour which is simple closed contour, then apply Cauchy-Goursat theorem that integrations over this simple closed contour is 0, and then use the properties of your contour integrations to conclude that this is true. That's exactly I have written. Now to see this, so this is the idea. To see this, consider the curve gamma t, which is exactly this gamma, which is gamma 1 of 2t. So t runs from 0 to half, and if you have another one, let be eta t. Eta t you can say that it is minus of gamma 2t. You can prove that this is actually eta t. This is nothing but minus of gamma 2t. Okay, so this is a parameterization. So gamma eta of t, which is gamma 2 of 1 minus t, t runs from half to 1. Now look, I have written, we have just reversed the directions of gamma 2 and joined with gamma 1. That means you start from Z1, go to Z2, instead of gamma 2 you consider minus of gamma 2, because minus of gamma 2 starts from Z2, ends at Z1. So then if I have this gamma, So gamma will be a simple closed curve. So therefore by Cauchy-Goursat theorem this is 0, and by the properties of contour integrations, so I can, since gamma is a union of gamma 1 and eta, so this is plus gamma 1 plus integrations over eta, but eta is nothing but negations of what is, so therefore this will implies integrations over gamma 1 which is minus of integrations over eta, but minus of integrations over eta which is exactly equal to integrations over gamma 2, because eta is nothing but minus of gamma 2, that's it, nothing else. Okay, because gamma 2 I am moving from Z1 to Z2, eta is minus gamma 2, that means Z2 to Z1. So therefore if it will have that, so we will get the results. Okay, so therefore if my function is analytic in a simply connected domain, then I have a Cauchy-Goursat theorem, and that theorem ensures us that if I take any 2 points Z1, Z2, then whatever contour I can take starting from Z1 ending at Z2, the corresponding contour integrations value will be same. That means it is independent of the choice of the contour. Now just the same thing I have just by drawing picture. So if you have Z1, I have Z2. So this is my C1 starting from Z1 ending at Z2. C2 is integration starting from Z1 ending at Z2. So now you consider Z1 to Z2 C1, and now C2 star. C2 star is nothing but minus of C2. Okay, so this is one of the way. Another way you can say that, well, the way you have considered C1, C2, actually it is actually simple, right? Simple closed contour. But I can take Z1 and Z2 like in this way. Suppose this is my C1 and suppose this is my C2. That means C1 and C2 will have a kind of some intersecting point. In that case, what should I do? Because in that case, it is not a simple closed contour. So that means what will happen? So there also it is true, because if it intersects finally many points, then what you do, you break this kind of object, this, and this, and each time it is simple closed contour. So 1, 2, 3, 4. So therefore I can have the curve gamma which is C1 union minus of C2, but which is not simple closed, because it is not simple, because there are cross are there. So but I can break this new contour which is C1 union of minus C2 into 4 pieces, and each pieces are simple closed contour sitting inside. There I will apply what is called Cauchy-Goursat theorem, and since it is finitely many, I can add it, and altogether the sum will give you 0. So therefore you do not worry that if C1 and C2 has a intersection. So then you can just break up into small pieces, make a simple closed contour and apply Cauchy-Goursat theorem. Okay, so that's what it is. So let C1 and C2 be two paths joining Z1 and Z2 having no points in common. That is crystal clear. You can easily do that because this C1 and C2 has no points common except Z1 and Z2. Then what you have to do, C2 star is equal to minus C2, that means opposite to the curve C2. Now consider a new curve C which is C1 minus C2, that means first take C1 and then take minus C2, which is a simple closed curve. Now since my f is analytic inside C, so therefore by Cauchy-Goursat theorem this is 0, then this means integrations, contour integrations of f over C1 minus C2 is 0. Then by properties of contour integration, this is integrations over C1 plus integrations over minus C2, but integrations over minus C2 which is nothing but minus of integration over C2, and that will give you this one. So therefore this is true if C1 and C2 has no point in common except Z1, Z2, but this picture tells you that if C1 and C2 have like even for infinitely many points common, you do not worry. So you have to just make into kind of pieces, and each pieces it will be a simple closed contour, and you apply Cauchy-Goursat theorem and you just have the results. Okay, now once I have what is called independent of the choice of the contour, now then I can talk about what is called indefinite integration. Now looks, now existence of antiderivative. Now if f is analytic functions on a simply connected domain D, then there exists a functions capital F which is analytic on my domain and capital F prime is equal to F. Now you can easily say, because my function is analytic on a simply connected domain, so therefore you can define capital F. Now you see I have defined. So fix a point Z0, define this kind of object. F of Z which is integration Z0 to Z FW dW. Now this makes sense. Even if I think about this as symbol, what is the meaning of that? So if this is my domain, this is my point Z0, this is my Z. So what is the meaning of this Z0 to Z FW dW? It says that take any contour C. This is nothing but integration C FW dW. That's it. Because since my function is analytic, D is simply connected, whatever contour I can take starting from Z0 ending at Z2 will give you the same value I just discussed by Cauchy-Goursat theorem. So therefore this kind of object makes sense. So therefore for each Z it will give you a single value. So therefore capital F is well defined. Okay, so therefore once capital F is well defined, the next part is so that yes, this capital F is differentiable and the derivative of capital F is exactly equal to small f. That means small f possesses what is called antiderivative. Okay, so therefore Cauchy-Goursat theorem will be very useful to talk about the existence of antiderivative of primitive of my function small f. So first observation is that once I have a Cauchy-Goursat theorem, that means given functions f is analytic on a simply connected domain, that means if I fix 2 points, the corresponding contour integrations is independent of the choice of the contour. Once I have that one, then I can define this kind of functions. It is well defined functions. The next part is to show that this capital F function is differentiable and derivative is small f. So how to do that? It says that now the integral is considered as a contour integral over any curve lying in D and joining Z with Z0. That means starting from Z0 ending at Z. By the first part of the integral does not depend on the curve we choose, and hence the function's capital F is well defined, because by Cauchy-Goursat theorem whatever contour I can take starting from Z0 ending at Z, the contour integrations will be independent of the choice of the contour. So therefore capital F is well defined. Only part is remaining to show that capital F prime is equal to F. But you just check that capital F is differentiable. Use the principal definitions. That means you just calculate f of z plus h minus f of z divided by h, calculate the limit h approaches to 0 and show that it is limit exists and limit is exactly equal to small a. So do some algebra. So what is capital F of z plus h minus capital F of z? This is the expression. That means this is z0 to z plus h fw dw minus z0 to z fw dw. One can have it that this is nothing but integration z to z plus h fw dw. But you should be always careful. You do not do the algebra the way like a to b fx dx, which is same as integration a to c fx dx plus integration c to b fx dx, where a is less than c less than b. Don't do this kind of algebra, because this is no more valid, because complex number there is no ordering. So therefore to have the meaning of this difference is exactly equal to this one, that means you have to say that yes, I have a point. So look, this is my domain. So I have a point z0, I have a point z, and I have a point z plus h, right? So therefore z0 to z means whatever contour I can take, this is the corresponding value of the contour integrations, integration c fw dw, right? And what is z0 to z plus h? That means this is the corresponding contour integration. Suppose this is c1, this is c2. So this is c1, this is c2, right? fw dw, right? And what is this? Now I have a point z, I have a z plus h. So therefore I am taking a contour c3. So therefore this is same as integration c3, what is called fw dw. So that's why you have to do that. So that means the difference is exactly equal to this one. That means now you can do the algebra, right? So now look, so what you have to do, so I have a C1, I have a C2, I have a C3. So that means you have to consider C, which is C1, okay, then union C3, and then union of minus C2, right? So therefore now the contour C, which is starting from Z0 going to Z by C1, C1. Then from Z to Z plus H, I will have C3, Z to Z plus H. And then Z plus H to Z0, that means C2 is taking Z0 to Z plus H. So therefore minus of C2 is taking Z plus H to Z0. So now this contour C is a simple closed contour sitting inside D. So therefore by Cauchy-Goursat theorem, integration C fw dw is 0. Then by do the algebra, C is nothing but is this one. So therefore you can break this integration into 3 contour integrations. One is integrations over, so therefore it will have integrations over C1 plus integrations over C3 plus integration over minus C2. This is 0. And that will tell you that integrations over, so this, so that means you can have it. You can say that this is 0. So therefore I can say that. So this is, so this will implies integrations over C1 plus integrations over C3 plus integration over minus C2 is 0. So that means what? That means you can say that just, integration over C3, right? Yes. So therefore you can say that integration, so this will implies integrations over C3, which is same as integrations over C3. C3 means I have Z to Z plus, integration over C3, it should be integrations over minus C2 minus integrations over C1, okay? So C1 means Z0 to Z, okay? So therefore it's fine, perfectly all right. So therefore you can say that, is it okay? Z0 to Z, yeah. So therefore integrations over, so this one, so this is minus of integrations of C2 minus of integrations over C1. So if I do this kind of algebra, you will have this kind of object. So this is integration over C3, C2 minus C1, na? So integrations over, okay, that's fine. So therefore I can do the algebra, fine. So okay, hold on, maybe I can calculate it explicitly, do not worry. So this is 0 is given, right? So therefore what? Integrations over C1 plus integrations over C3 is exactly equal to minus of integrations over minus C2, that means integrations over C2. So therefore integrations over C1 plus integration over C3 is equal to integration over C2. Do some algebra. So therefore this will implies integrations over C3 is integration over C2 minus integration over C1, and this is exactly this one, integration over C2 minus integration over C1. So therefore, even though it looks like a priori, that means I am doing this kind of business, like you know, in case of real analysis, integrations A to B I can break into two parts, A to C and C to B. But this kind of observation, you can think in your mind and do that. But do not kind of think that the same technique in the real analysis, what you know, you can have it in the case. But here the things are different. So this is a symbol you can think about. That I have to see integrations or contour integrations over C2 starting from Z0 and to Z plus A. Similarly here, and apply Cauchy-Goursat theorem, and then you will have this kind of equations, and that's how it is the corresponding meaning. So therefore at the end we will have this expression f of z plus h minus f of z, which is exactly equal to this expression. Okay. Now what is this? This is z to z plus h, that means so this is nothing but some contour integrations fw dw, where this contour C starts from z ending at z plus h, whatever contour. So you take this very simple kind of contour. So you have a z, you have a z, you have a z plus h. So you just take the straight line starting from z ending at z plus h. So where the curve joining z and z plus h can be considered as a straight line L of t, z plus th, because this is the corresponding parameterizations, because it is independent of the choice of the contour. It doesn't matter which contour I can take. So I am just considering the straight line for my calculation purpose, because at the end of the day I have to show that capital F is differentiable and derivative is small f. No? So this is the kind of estimation. So now f of z plus h minus fz divided by h minus what is called fz, this expression which is exactly equal to this one. You just compare with the real analysis technique, same things it working here. Okay. So I think this is 1 by mod h. Okay. So this fz plus h minus fz expression you know. So this is z to z plus h fw dw, that is okay. But this fz, I can say that f of z, which is nothing but integration z to z plus h, what is called fz, na? So fz dw. Because fz will come out, it's a constant. So therefore f of z, then you will have z to z plus h dw. Now what is this object? This will, you can just calculate, this is actually give you h, fz times h. That's how I have written. And what is that? This is very easy, because what contour I am considering. So this is nothing but integrations over your what is called line segment LT, right, of dw, because what is the integrand? Integrand is constant functions 1. So and what is the formula for, what is the definitions of this contour integration? This is nothing but integrations. What is this? This is 0 to 1, right? So that means this is 0 to 1. F of gamma t, so f of gamma t is 1 because constant function is 1, and then L prime t dt. What is L prime t? L prime t if I have h. So therefore it is h dt, and that means this is h. So therefore this is, so therefore if I adjust it, so for fz I am writing in this integrations form, and then I will have 1 by h. So 1 h factor is there, 1 by h get cancelled. So therefore 1 by mod h will come out. So you will have 1 by mod h time this object. So here I have used this fact that integrations L dw is h, because here the integrand is 1 using the contour integrations. Now you have to use the fact that f is continuous. Now since f is continuous at the point z, so therefore epsilon delta definitions, given epsilon I should have an existence of delta such that f of z plus h minus fz I can make less than epsilon whenever mod h is less than delta. So therefore if mod h is less than delta, so therefore 1 by modulus of h times this object, which is, now you see I can have what is called ML formula. That means this kind of absolute of the contour integrations I can estimate it by m times L. So what is this object? So this is nothing but integrations over the contour integrations LT f of w minus f of z, f of w minus f of z dw, right? So So if I want to estimate this one, what is the estimate? This is dominated by supremum of the integrand times length of the curve. Now what is the length of the curve? If I just calculate it, this is, so a length of the curve means integrations. If L is the parameterization, that means integration 0 to 1 mod L prime t dt, right? And what is L prime t? H. So that means mod h. So length of the curve is mod h. That is okay. And what is m? M is the supremum of the integrand. That means absolute of f of w minus f of z, right? This mod. And what is f of w? W runs from z to z plus h. And what is the z to z plus h? So that means if I have z to z plus h, so distance between w minus z, which is always dominated by what? Mod h. And mod h is less than delta. Now if mod h is less than delta, that means the distance between w and z, this is less than delta. So therefore the continuity f of z plus h minus f of z, that means f of w minus f of z, which is less than epsilon. So therefore the supremum is less than epsilon. So therefore m is less than epsilon. So therefore you will have, so this is by ML formula, this object is dominated by m times mod h divided by mod h, but m is the supremum which is less than epsilon. So therefore this is less than m times, or sorry, epsilon times mod h divided by mod h. So that means this is epsilon. So therefore I can say that I can make the distance of f of z plus h minus f of z divided by h minus fz, which is less than epsilon, and epsilon is arbitrary. So therefore if I take the h approaches to 0, so this limit is exactly equal to f of z. Okay, so this is the one. So first what you have to do, so first you have to define what is your function is capital F, that is okay. Next part you have to do that's capital F is differentiable. So that is why you have to just calculate what is f of z plus h minus f of z. Then you just estimate this object. That means I will show that capital F is differentiable and derivative at the point z is small f. So therefore you say that capital F of z plus h minus fz divided by h minus fz, I can make this object very small. To do that, you have to use this fact that integrations over LT dw is h, adjust or do some algebra. This estimate is exactly equal to this one. So that means I have to estimate this object. Now this is 1 by mod h will come out. It will not affect the integration. The integrand, this is same as integrations over, because z to z plus h, I am considering the contour straight line joining z ending at z plus h. So this is becomes the contour integrations over LT fw minus fz dw, and you know the contour integration is dominated by m times L. What is L? Length of the curve. Length of the curve is modulus of h. You can have it because it is a straight line. And what is the integrand? The supremum of fw minus fz absolute if w runs over the line segment z to z plus h. If I take w here, then you can easily say that w minus z, which is always dominated by mod h. And since mod h is less than delta, so therefore w minus z is less than delta, by continuity modulus of fw minus f of z, which is less than epsilon. So therefore the supremum of the integrand of the absolute of mod fw minus f of z, which is less than epsilon, that means capital M is less than epsilon. So therefore you will have this object. That means this object is epsilon times mod h divided by mod h. So one mod h will be there in the denominator, and this is coming from ML formula. So therefore h get cancelled. So therefore I can estimate this difference is arbitrarily small. So therefore this limit exists, and which is exactly equal to small f. Okay, so that's the meaning that if my function is analytic on a simply connected domain, that means it possesses antiderivative, and this is the combinations of all whatever I have discussed. 3 theorem, if I combine it, this is the conclusions. It says that suppose you have a function f which is continuous on a simply connected domain, this is very important, then the following statements are equivalent. Number one. What number one? The integral of f along contours lying entirely in D and extending from any point z1 to any point z2, all will have the same value. That means it is independent of the choice of the contour. As long as my contour starting from z1 ending at z2, all the what is called contour integration will exist and they will have the same value. Number two, f possesses antiderivative, because once I have the independent of the choice of the contour, you can define this kind of functions, f of z, z0 to z, f of w, dw, and I have just proved that this is differentiable and this is f. That means small f possesses antiderivative, this is okay. And third one is that integral of f around any closed contour all have value 0. That means this is the Cauchy's theorem or Cauchy-Goursat theorem. Okay. So now, so if I have a Cauchy-Goursat theorem, it is extremely nice theorem. So as long as my function is analytic in a simply connected domain, then if I take any simply closed contour, the value of the contour integration is 0, which implies that if I take any point z1, z2 in my domain, whatever contour I can take starting from z1 ending at z2, the corresponding contour integral exists and the value will be independent of the choice of the contour. And 3 is that f possesses an antiderivative or primitive. So therefore, this is the kind of 3 equivalent criteria. So if my function is nice, if my domain is nice, so therefore f possesses antiderivative. If I take any simple closed contour, the contour integration is 0. If I take two fixed points z1 and z2, whatever contour I can take, the value of the contour integrations is independent of the choice of the contour. Okay. So that's all for simply connected domain. So like what is Cauchy-Goursat theorem and what is the consequence of Cauchy-Goursat theorem. In my next lecture, I will talk about Cauchy's theorem or Cauchy-Goursat theorem in multiply connected domain. So simply connected domain, that means there is no hole. That means your domain is very nice and my function is analytic. Suppose if I deal with some domain, suppose there is a hole and suppose my function is analytic, then what sort of theorem you can expect in case of Cauchy-Goursat theorem for analytic functions in a multiply connected domain. Okay, so in my next lecture I will talk about Cauchy's theorem for multiply connected domain. I think I should stop here. Thank you.